Okay, so we talk about the DES decryption. So we have seen the DES. So encryption was like this. So we have a plain text X. We apply a IP. We apply a permutation on this. Then we divide this into two part. L0, R0, 64 bit. 64 bit is 32 bit, 32 bit. Then we are having a Feastel operation. So this is directly coming here, L1 R1. Then this is the function f, which is taking K1 as the first round key. Then we are XORing with this. We are XORing with this. Bitwise XOR, and this is the R1. Okay. So this is the first round, and then we continue this. So from here we have L2 R2, the same Feastel structure we are applying with K2, then we are XORing. So this way we continue up to we got L16 R16. So 16 Feastel cipher we are applying, then finally we are adding the IP inverse. And we got the Y, the ciphertext. So this is the plain. This is encryption of DES. DES encryption. Okay. Now the question is how the Bob decipher it. So Alice and Bob. So Alice wants to send a message to Bob. So they agreed with the common key K, whose effective size is 56 bit. Okay. And Alice has a plain text M, whose size is 64 bit. So they decided to use the block cipher DES. So Alice is doing this encryption. So this is X. Alice is doing this encryption and getting this Y and sending Y to Bob. Now, so Bob has to decrypt it. So how Bob can get back the message? Decryption. That is the decryption algorithm or decryption procedure. So from this Y, Bob has to get back X. So basically Bob will apply this is IP inverse, IP, go back here. So basically we have to invert the Feastel cipher. So if we can invert the Feastel cipher, if we know how to invert a Feastel cipher, then we are done. So the question is how we can invert a Feastel cipher. So suppose we have a one round DES, which is basically a Feastel cipher. So this is basically we have L0 R0 and the output. This is one round DES. So this is L1 R1 and this is basically F. This is K1 for the first round, and we have XORing, and this is R1. So basically L1 is basically R0 and R1 is basically F of R0 K1 XOR with L0. This is the encryption. Okay. Now we want to decrypt. We want to make it reverse. I mean, so for decryption, our input will be L1 R1. So this is our input L1 R1. Now we need to get the L0 R0. So this is the decryption process we want to mount. Okay, so how we can do that? So from this equation we can say R0 is basically L1. So L1 is basically R0. Now we need to get L0. So L0 is basically what? L0 is basically R1. If we XOR both sides with F of this quantity, then the XOR this and this XOR will cancel out. So basically we have R1 XOR with F of R0 K1. So, what is R0? R0 is nothing but L1. So, this is basically R1 XOR with f of L1 K1, that is it. So, that is R1. So, we just apply f on this with the value K1, the round key, and then we XOR with this with R1 bitwise XOR, and this is our L0. So, we got both L0 and R0 from L1 and R1. So, this is the one round decryption method of Feastel cipher. And the beauty of this cipher is we are not inverting this f, we are applying same f, because sometimes inverts may not be possible, because we in the f function we have S box, we have some permutation. So, that S box is also from 6 bit to 4 bit, if you remember DS S box, that is a 6 bit to 4 bit. So, that is also difficult to invert. This is one of the S box in. So, if we had to invert f, if we had to find out f inverse, then it may not be always possible, it may not be injective itself also. So, in that case inverse may not exist, then we have a difficulty, but the beauty of this structure is, beauty of this Feastel structure is, we really do not need to invert f to get the decryption process. So, we just apply f again and we get the cipher, we get the plain text. So, this is the inversion of the Feastel cipher. So, basically for DS we will apply this inversion process, and for that we need to have same keys, this K1, K2, K16. So, the Bob has to generate the key seedling algorithm and get the round keys, and Bob will do the same process to invert this Feastel cipher, and finally, Bob will reach here. After reaching here, Bob will apply the IP inverse to get the plain text X. Okay. So, this is the DS decryption. Now, the question is, we want to analyze this block cipher DS in the security point of view, how secure this DS is, whether we should I mean what type of attacks can we think on DS. So, that is called cryptanalysis on DES. Cryptanalysis on DES, or that is, or attacks on DES, something like that. Okay. So, there are some issues with DES. The first issue is it is not well documented, in the sense that the S box, main problem is with the. So, this is the problems with DS S box. So, they have given the just the table, a table, and a 4 by 16 table, 4 cross 16 table, 1 2 3 0 1 2 3 like that 15. So, they have given, say this is S1. So, there are 8 such S box. So, they have just given S box in a table and we need to do the table lookup, but how these values are coming, there is no proper explanation for that. So, that is one of the drawback of this, and another issue is with the key size. So, key size of DES is just 56 bit effective key size. So, that will enable us to mount the attack like generic attack like exhaustive search attack, time memory trade off attack. We will come to those attacks, those are generic attack. So, what do you mean by generic attack, non-generic attack? We will discuss that. So, but before that, let us talk about what are the attack model we have for the cryptographic cipher. Okay, so before that, so we want to so what are the attack model we can think of a cipher. So, first one is known ciphertext attack. Or this is called ciphertext only attack, ciphertext only attack. So, the point is Alice and Bob, they are communicating with each other and the ciphertexts are placed into the public channel, and Oscar, the bad guy, I mean the attacker, you should not say bad guy, attacker is sitting here and Oscar has full control on this channel. So, Oscar is hearing all the ciphertexts, Oscar is getting all the ciphertexts. So, that is called ciphertext only attack. Oscar is having only the access of this channel, and so Oscar is getting the ciphertext which is between Alice and Bob, or all the old ciphertext between Alice and Bob. So, that is the this model, and the next model is known plain text attack. Known plain text attack. So, in this attack model, Oscar is having some plain text and the corresponding ciphertext. So, the attacker has some plain text and the corresponding ciphertext for some. So, there are n of such thing. So, attacker has some plain text, maybe some old plain text and the corresponding ciphertext, which Alice and Bob are not currently using that plain text, but it was used long time back. So, there is no much importance on that. So, they make it public kind of thing. So, they have given this plain text and ciphertext, and the goal of this attack is, so they are using a common key k. This is the symmetric key setup, they are using a common key k. So, the goal of this attacker is to get the key k or to get the, so suppose they are now using the message P star, the new message, and getting the C star. So, or to get or to guess the new plain text P star from C star. This is the current plain message they are communicating. Current message is P star and the corresponding ciphertext is C star. So, C star Alice is sending to Bob over the public channel. Now, Oscar is hearing C star and Oscar is having some old messages, some PICI, some old message and corresponding ciphertext, plain text corresponding ciphertext. So, the goal of the attacker is to guess the current message and guess the or get the key. That is also a big challenge to get the key. So, this is one model, and another model is chosen plain text attack. This is called, sorry, this is, just love this. So, this is called chosen plain text attack. This is the third model, chosen plain text attack. Okay. So, here what we are doing, we are giving some more power to the attacker in a sense that, so attacker can choose some plain text and get the corresponding ciphertext. This plain text can be chosen by the attacker. So, attacker or the Oscar can choose the plain text and get the corresponding ciphertext. So, as if this encryption machinery, we are giving the temporary access of this encryption machinery to the attacker without revealing the key. So, what we are doing, we are inbuilting key over here and we are giving the access. Say in software, this could be a encrypt.exe, I mean des.exe, des encryption.exe. So, we inbuilt the, we are not revealing the key is inside. So, but we are giving the temporary access of this encryption machinery to the attacker, so that attacker can choose the plain text P1 and can get the ciphertext C1, P2 can get the ciphertext C2, like this for some point of time. Then we remove this access. So, we are giving the temporary access of the encryption machinery to the attacker without revealing the key. So, key is inbuilt some sort of. So, attacker can give the plain text and can get the corresponding ciphertext. So, that is this model, and the goal of the attacker is to get the key, that is the and or the P star, to guess the P star, which is the current plain text between Alice and Bob, P star from C star. Okay. So, this is the goal of the attacker in this attack model. Okay. Now, next one is chosen ciphertext attack. So, this is chosen ciphertext attack. Okay. So, in chosen ciphertext attack, we are giving the temporary access of the decryption machinery to the attacker. So, like this is a DES decryption function, So, key is inbuilt, key we are not revealing to the attacker. So, we are giving the temporary access to this machine to the attacker. So, temporary access to this decryption machinery to the attacker, so that attacker can choose a ciphertext C1 and get the corresponding plain text. Attacker can choose another ciphertext P2, like this. So, attacker can generate this CI PI pair. So, this is chosen by the attacker, this ciphertext, and then we remove this access from this attacker. So, we are giving the temporary access to this decryption machinery to the attacker, and we have removed that access, and then after that the goal of the attacker is to obviously to get the key or guess the key, and to get the to know what is currently going on between Alice and Bob. So, what is the new message or the plain text from the ciphertext sister. So, this is the chosen ciphertext attack. Okay. So, now we will talk about the exhaustive search attack on DES. So, we talk about exhaustive search attack on DES. Okay. So, this is so DES is a block cipher which is taking a 56 bit effective key. This is the encryption of DES encryption. Okay. So, Alice encrypt using this and Alice send this. This is P and this is C. Alice send it to Bob. Okay. Now, the key size of the DES is 56 bit. Length effective key size is 56 bit, and that will mount as a this exhaustive search attack on DES. So, how? This is basically a known plain text attack. Suppose Oscar, the attacker, knows this, a plain text and the corresponding ciphertext, and attacker wants to guess the key. Okay. So, attacker don't know the key. So, attacker wants to guess the attacker doesn't know the key. So, attacker wants to guess the key. So, what attacker will do? So, attacker know a plain text and the corresponding ciphertext. This is kind of known plain text attack model under. So, what Oscar will do? So, Oscar knows the key is 56 bit. So, key is a typically a 56 bit 01 bit say. Okay. So, this is the key space. So, what is the size of this key space? 2 to the power 56. So, if 1, then we can say K1, K2 like this. So, these are the keys K1, K2, K3 like this. So, K 2 to the power 56. These are the possible keys. This is the key space for DES. Okay. Now, what Oscar will do? Oscar don't know the key, doesn't know the key. So, Oscar will try for all possible key. This is called brute force or exhaustive search. So, Oscar will try for. So, Oscar have this C, or then Oscar will do the DES decryption algorithm. These algorithms are public. This block cipher algorithms are public. Only secret is the secret key K. Okay. So, our encryption algorithm is public, encryption decryption algorithm what we are doing, those are public. Only secret thing is the secret key K. Okay. So, so what Oscar will do? Oscar will try for K1 and decrypt it and see getting a P1 and check whether this P1 is P or not. If it is P, then okay, fine, that is the corresponding key is K1. So, this way Oscar will try for all possibilities K2, K3, Ki and get corresponding Pi and check whether Pi is matching with P or not. So, this way Oscar will try for all possible keys, and once it is matching with this P, then it stop. It could be other way also, encryption also. Oscar can encrypt P and check whether Ci is matching with C or not, because Oscar is having a PC pair. Okay. So, now, so this is the exhaustive search attack on DES. So, it will search for all possible keys in a key space. So, then what is the time complexity for this? So, time is basically so we have to, worst case we are getting the key at the end. So, time is basically 2 to the power 56 size of the key space and time required for DES encryption or decryption. Time required for DES encryption or decryption. So, if you assume our machine is fast and this DES encryption decryption time is a 1 second. So, this is basically 2 to the power this many second. 2 to the power 56 second, which is huge, which is maybe how many? I mean, it's few years. Okay. So, that way we cannot do the exhaustive search on DES. So, what is the next step? Now, suppose we have two two computer and we divide the key space into two parts and we ask both the computer search in this part in parallel. So, in that case the time will be reduced by half because they are working in parallel. So, time will be reduced by 2 to the power 55, which is not much benefit, but if we have more than two computers, if you have many processors, so if you have say 2 to the power 32 processors, and then what we do? We partition this key space into that many number of partition, and then we ask each of this computer, each of this processor to search in this particular region. So, we are partitioning this key space into this region and we will ask the computer, we will ask the processor. So, this is the parallel computing. So, processor are running in parallel and they are searching in their respective key space, and once somebody got the key, so it will send a signal that hey, I got the key, so stop. So, whole system will stop. So, this way if there are 2 to the power say 36 or 32 processors, 32 computer or processors which are running in parallel to find the key, then the time will be reduced by 2 to the power 56 by 2 to the power 32, which is basically 2 to the power 24. So, which is this second, which may be less than 2-3 days or something. So, this is an attack. So, this is an exhaustive search attack on DES. So, this attack was so Electronics Founder Foundation EFF, they mount this attack in 1996 and they build a hardware for this attack and they have spent around USD 2 lakhs and they can and their time complexity for get the key is just a less than 3 days, I think. Time is less than 3 days. So, this is an exhaustive search attack on DES. Okay. And this is a hardware implementation by the Electronics Founder Foundation, and there are many softwares in software implementation on finding this exhaustive search attack on DES. So, DES is broke, and this attack, this type of attack, exhaustive search attacks, is called generic attack. Why? Because here we are really do not bother about the inner design of the DES. We do not care how the inside it is the design, we only do care about the key space. So, this same attack can be mounted on another cipher, which may be some X block cipher or maybe some Sourabh block cipher, Only thing, if the key size is 56, then the same attack idea will be carried over here. So, we are not really looking at the inside of this cipher. So, that sense it is called generic attack. Okay. And there are some non-generic attack on DES. So, those are basically those ones. In those attack we want to see the is there any relationship between the plain text and the ciphertext, linear attack, is there any differential between the plain text and the ciphertext, or some after some round. So, those are differential attack. So, those are basically non-generic attack. So, non-generic attack. So, generic attack is basically exhaustive search or the time memory trade-off attack. We will discuss the time memory trade-off attack later on. So, non-generic attack are basically linear cryptanalysis, linear attack, then the differential attack, and then some version of differential attack like boomerang attack, impossible differential attack. So, in this attack model we will really need to see the inner design of the cipher, and we are really need to find out some linear relationship between the plain text and ciphertext. So, that way these are non-generic attack. So, these are cipher specific. So, there are very well non-generic attack available for DES. So, DES is attacked by the linear attack, DES is attacked by the differential attack, and there are other non-generic attack which are present in DES. So, DES is broke in the sense of generic and also in the sense of non-generic. So, we will look at some alternative of the DES. We will talk about triple DES in the next lecture. Thank you.